And thank you very much for the opportunity to give a talk here. And also thanks for Eriko Hironaka for giving already a good introduction for pseudo-Anosov mapping classes earlier. So this talk will be more of a topology talk also, but there will be quite a bit of algebra, polynomials, and even some stabilization theorem for the algebraists. So we denote by SG the closed orientable surface of genus G, and by mod S the mapping class group of SG, which is the orientation preserving homomorphisms of SG up to isotopy. And again, we have this Nielsen-Thurston classification of mapping classes. We have periodic, reducible, and pseudo-Anosov elements. And we also study pseudo-Anosov mapping classes, which once again, the topological intuition for pseudo-Anosov mapping classes that they are stretching the surface sort of like a rubber band. When you stretch it in one direction, it shrinks in the other direction. Also, from the dynamical viewpoint, you can think about the pseudo-Anosov. Pseudo-Anosov maps are ones that mix the surface really well. The other types sort of don't mix everything well. And we have the stretch factor associated to the mapping class, which tells us how much we stretch the surface and how fast this mixing happens. And also we have other meanings associated to lambda. It's related to the entropy of the representative maps, translation distance on Teichmuller space, and also the volume of the mapping torus, which is a hyperbolic three-manifold. So this is kind of the motivation to study stretch factors. The general properties of the stretch factors, sort of the two most important ones, is that every stretch factor is an algebraic unit, and all Galois conjugates of a stretch factor lambda lie in this annulus between 1 over lambda and lambda. And conversely, it's been conjectured that every real number satisfying these properties is a pseudo-Anosov stretch factor. So since understanding all pseudo-Anosov stretch factors seems pretty hard, we might just try to understand the simplest ones, the minimal stretch factors on each surface. But this is still pretty much a hard task. The results are only known in a few special cases. Another way of study sort of the complexity of stretch factors is by their algebraic degrees. So Thurston showed that on SG, every pseudo-Anosov stretch factor has degree at most 6G minus 6. And if the invariant foliations are orientable, whatever that means, then we have a lower bound 2G. And it turns out that this sort of algebraic complexity have implications to topology. So if you have the lowest stretch factor possible, quadratic stretch factor, then it turns out that this pseudo-Anosov comes from an Anosov map of the torus by branch covering. So these are pretty simple maps. So if you have low degree, that means you're topologically very simple. Later on, Long showed that if the degree is odd, then the degree must be bounded by 3G minus 3. And Thurston said in his paper that the maximum 6G minus 6 can be realized by his construction, but he didn't give a proof. So then Margali asked, how can we get the 6G minus 6? And in general, what are the possible degrees that can occur on SG? And his student, Hyun-Sik Shin, showed that the theoretical maximum 2G is realized in the orientable case. And he also did lots of computer experiments, and he conjectured that all even degrees from 2 to 6G minus 6 can be realized. And in the rest of the talk, I try to give a flavor of the proof of fact, and that every even degrees in the orientable case less than 2g are also realized by some examples. So our construction uses Penner's construction that goes as follows. So we take two multi-curves on the surface. So multi-curve is just a disjoint union of simple closed curves. We have A, which is the collection of red curves, and B, which is the collection of blue curves. Moreover, we require that this pair of multi-curves is filling, which means that if you take any non-trivial curve on the surface, at least one of these will intersect it. Okay, there's no way to escape any of these curves. And then we apply Dane twists about these curves. So we cut the surface along a curve, we twist it in the positive or negative direction and glue it back. So the statement is that if I apply Dane twists, positive Dane twists about the red curves and negative Dane twists about the blue curves, and I use all these Dane twists at least once, all of them at least once, then I get a pseudo-Anosov mapping class. So the intuition is that if you make such a product, it will mix the surface well, right? So if you take any curve, eventually one of these curves will hit it, and it maps it to something else. So it will mix the surface well. So the good thing about Penner's construction is that everything is very well translatable to linear algebra. So it turns out that if I'm interested in stretch vectors of pseudo-Anosov maps arising from Penner's construction, I can just do linear algebra. So we denote by n the intersection matrix of the multi-curves. So in the previous case, we had 3 and 2 multi-curves, so it's a 3 by 2 matrix describing the pairwise intersection numbers of red and blue curves. And it turns out that the action of each Dane twist on these 5 curves can be described by a matrix using only this intersection matrix. So it doesn't matter, the topological setting doesn't matter, only the intersection numbers. And so if I make a product of these matrices Qi, they describe the actions of the Dane twist products on A and B. And it turns out that if I use all of my Dane twists at least once, then I get a pseudo-Anosov map. And the stretch factor is exactly the Perron-Frobenius eigenvalue, which is the largest eigenvalue of this product. So all I need to do is look at these matrices Qi depending on the intersection matrices and study the eigenvalues of these products. So the idea is that just looking at one specific pseudo-Anosov, it's not easy to tell what the degree of that pseudo-Anosov is. So I'm going to look at a sequence of pseudo-Anosov maps and try to say what the asymptotic degree of this sequence is. So in Penner's construction, we can make two choices. One choice is I can choose the pair of multi-curves. And the other choice is once I have the multi-curves, I can choose the product of Dane twists in some way. So maybe the convenient choice would be to fix a pair of multi-curves and then vary the Dane twist product. But we're going to do the opposite. So we fix the Dane twist product, and then we vary the pair of multi-curves in a way that we fix one of the multi-curves, A, and then change the other one by a third Dane twist. So I have my red curve and blue curve, and I fix my red curve, but the blue curve becomes more and more complicated, sort of more and more entangled with with the other curve. And first, it seems like it doesn't make sense to fix the Dane twist because the underlying curves change. But the way I mean it is, if you have a Dane twist product about the red and blue curves, the blue curves will have images under these Dane twists, right? So you can associate to each Dane twist the corresponding Dane twist in the other pairs. And it turns out that the intersection matrices of these red and more complicated blue curves have a really nice property, and is that their intersection matrix is asymptotically linearly growing. So they become more and more entangled in a sort of well-controlled way. So the pairwise intersection numbers of each blue and red curve increases linearly up to a bounded error. Moreover, we specialize to special sort of Dane twist products which, by which we mean that we take a red one and the blue one and the red one and the blue one. So this is an alternating Dane twist product. And we formalize it as follows. So we define this bipartite graph G and M on the partition 1 to n and n plus 1 to n plus m. So first partition corresponds to the multicurve A, and second to the multicurve B. And vertices in this graph correspond to the curves in the multicurves. And then I take a closed path in this bipartite graph, which bounces between the two partitions. So I get an alternating sequence of red and blue curves. And then I create this product of the QI. Now this is now only just a formal product. I want this to be a matrix, but remember that the QI depend on the intersection matrix. So I need to specify my intersection matrices, and I'm gonna take this sequence of intersection matrices corresponding to my sequence of curves, and then define my matrices MK using this sequence of intersection matrices. So geometrically what I have this fixed red curve and more complicated blue curves. So, and I construct these pseudo-Anosov maps from all these pairs, which become more and more complicated. These MK are the matrices that describe these pseudo-Anosov maps. So as you can imagine, these pseudo-Anosov maps become more and more complicated, which means that their stretch factor go to infinity. And also, MK has reciprocal characteristic polynomial. So 1 over lambda k is also the root of the characteristic polynomial. So in a way, these maps get out of control. But what I do is I take all the other eigenvalues of the matrices MK and just look at the span of their eigenspaces. So it's all other eigenvalues lie between this annulus between 1 over lambda k and lambda k. So I call this the middle invariant subspace of MK. This is a codimension 2 subspace of the Euclidean space. And then these are invariant subspaces, so there's some induced map by the matrices MK on these subspaces. An interesting thing is these subspaces eventually stabilize. They converge to some fixed subspace. And also the maps on these subspaces also converge to some limit map. Moreover, these limits don't depend on the homotopy class of gamma. There's some technical condition, but basically they are invariant under homotopy of gamma. So gamma was the way of choosing these Dane twists. And finally, we have this inequality between these two ranks. So the rank of f minus the identity is bounded by 2 times the rank of n star minus 2. So this means that if the rank of n star is low, then f has to be close to the identity. It has to have a lot of 1 eigenvalues. In particular, if the rank of n star is 1, then I have that my limit is the identity. So what happens is that I have this matrix MK, matrices MK, and their characteristic polynomials have roots that I have the lambda k going to infinity, 1 over lambda k going to 0, everything else going to 1. And it turns out that if you have a sequence of polynomials with these properties, then you can relatively easily understand how they factor over Zx. So you can control the algebraic degrees of lambda k. So the precise statement is that if the rank of n star is 1 and the rank of nk is r, if k is large enough, then asymptotically the degree is 2r. So asymptotically the degree stabilizes. So geometrically what we have is basically in order to get a rank 2r degree stretch factor, all I have to do is find a pair of multicurves such that their intersection matrix has rank r in some sense. And it turns out, using some arguments using flat surfaces and their cylinder decompositions, it turns out that the conditions of this theorem can be satisfied, and we are done. And finally, I'd like to finish with one problem and one question. So first of all, it would be interesting to have a non-asymptotic construction for these maps. At many places in this argument, we have to choose a large enough k. So some concrete examples would be nice. And it would also be interesting to know what's going on for odd degrees, because this argument completely fails for odd degrees. And it also might be that there is another abstraction for odd degrees. Experience of Yun-Chik-Shin showed that, or didn't show that there is a degree 5 pseudo-Anosov on S3. So maybe there's some other abstraction. And since probably everyone is getting hungry already, I'm going to stop here. Thank you. There's one over there.
So are there other boundaries invariants for these pseudo-Anosov besides the stretch factor?
What invariants?
Boundaries invariants?
Other than the stretch factors?
If I remember singularity type,
Yeah. I haven't thought about that. I don't know. So,
yeah, I have a conjecture about that. But there's a version of the unit. The idea is that if you're like a cubic stretch factor, like very low stretch factor, quartic instead of quadratic, then you should be a branch cover of a simpler thing. It's only going to be true, like if you say cubic, for hugely high units. In other words, if you fix a degree and say, what are all the things with a small degree? Are they all branch covers of lower things? You first have to say, look, our world has to be things that are 10 to the 10th degree. The genus is a